Oh, yeah, it's pretty funny. This, okay, let's get that. Yeah, okay. That's all because I'm a football watch, you know, like 100%. I heard it was very funny. My third. That's all. My current. Yeah, and I think you're just like, yeah, that's what it is. Learn the lesson or I just I didn't want to spit on it. Just didn't have like the land was steeper and longer. Good enough, but it was not for long. That's big. I don't think it's a double. That's what I'm saying.
Did you do like the Jerry type of? I like to share that.
It's here. This is right. I guess it's. Yeah.
Oh.
You guys is very important. It's low. This happened to me. But I just don't know about this. And then
All right, so here we are, end of a snowy week. So, couple things, well, one thing before we start, and well, maybe a couple. One is that just remember that assignment number 1 is due at the start of next class. So please just write out your solutions and then staple them together and you'll submit them at the start of Wednesday's class next week. The other thing is that I will make new tabs on the sign up document for the lab. So I'll do that today or this evening or something like that. And so there'll be an experiment 2 sign up. You can do that whenever you like, but what I'll try to remember to do is to make sure that you've signed up for experiment 2 before you leave the lab next week after finishing experiment number 1. Okay, so those aren't ready, those tabs aren't made yet, but I will do that today or tonight. Okay, so what we were talking about we were beginning to talk about distributions, and the idea was that you make a sequence of repeated measurements using the same type of method over and over and over again, and then you plot your results as a histogram. And the example we were talking about is maybe sitting next to a radioactive sample that's emitting electrons, and then you count the number of electrons that have been produced in a certain time interval, delta t, maybe 10 minutes or whatever it is. And so then you get 12 counts, 18, 13, 14, and then you put them in bins and you make this distribution. So what I want to talk about today is the types of things that we can calculate to characterize this kind of distribution. And I think they're familiar and easy, but let's just do that because we're going to make use of these results to do things that are a little more interesting, maybe. So the mean or average of the number of counts in this example is given by, so we could call it X bar for the average or the mean. And so it's going to be 1 over n, the total number of trials, times the sum of the individual results for each trial. And so this would just be, for shorthand, we'll probably not always write the summation intervals I equals 1 to n. If you see something like that, the sum is implied to be from I equals 1 to n. Okay, so that's easy to do. You just add up all these numbers and then divide by n, and that's the average number of counts, of course. And then you could also calculate the standard deviation. So the standard deviation, which we'll call S, is given by, okay, well, the square of S would be 1 over n minus 1, and it's going to be the sum from I equals 1 to n. And what the sum is going to be is the individual trials xi minus x bar, and then squared. What would you get if this wasn't squared? What would you get for the sum? Xi minus the average, and you can add them up for all your trials. What would the sum result in if there was no square here? Would it be negative or positive or what? Like half the time X should be less than the mean and half the time X should be greater than the mean. So yeah, it would just add up to 0. That's right. So because we'd be adding half the time positive results, half the time negative results, and they'd be distributed symmetrically about the mean. So this square, what it's doing is it's stopping this thing from being a negative number. So we're always adding positive numbers. Okay, anyway, so there's the square of the standard deviation. Now, if we go back to this plot here, we could label what these things are supposed to be representing. The average will sit approximately at the center of this distribution. And so this would be X bar, would be something like this. And then the standard deviation S tells us approximately how wide this distribution of results is. And so, you know, if all of your xi values are really clustered close to the mean, then this difference will always be a small number, and then you square it, so you add up a bunch of small numbers, and so your standard deviation would be small. And if your distribution is like you have X values spread out very wide, then some of these quantities are going to be large, and then you square them and add them to your sum, and that's going to expand the standard deviation. So S is telling us how closely clustered around the mean is our set of measurements. Okay, good. Now, in any real experiment, we can never hope to produce the exact distribution that you'd observe in a perfect scenario where you made an infinite number of measurements and you got a perfectly smooth distribution. All we can do is we can take a finite set of n trials to try to estimate what the true distribution would look like. And so the distributions that we measure are called sample distributions, and they're supposed to be approximations to the true distribution that you would get in the limit that you could take an infinite number of measurements. And that true distribution is called a parent distribution. So we're going to try to use a finite set of measurements to create a sample distribution that approximates the true parent distribution. So that's kind of the terminology that they might use in a statistics course. So if we were to take a large number of measurements, and by large, I mean the unrealistic case of n goes to infinity, then our so-called sample distribution which is formed from a finite set of n measurements, would approach the so-called parent distribution. And so this parent distribution is really the true distribution for n goes to infinity, which we could never know exactly. Oh, what happened here? The screen share ended unexpectedly. That's not good. Let's see if it comes back. Okay, good. So it's back. So with these definitions, what we can do is we can define the true mean. So the mean of the parent distribution is going to be mu. So do you guys got a question? So mu is going to be the limit that n goes to infinity of 1 over n times the sum of xi. So we just take our definition of the average x bar and just take it to the limit that n goes to infinity. That's all we're doing. And then we have the standard deviation of the parent distribution is going to be sigma squared is equal to the limit n goes to infinity. And now there's a little subtlety here. So what we had before was 1 over n minus 1 times the sum of xi minus the average. So we'll use mu for the average here. This is what you might naively guess, but it turns out that for the parent distribution, the standard deviation, or the square of the standard deviation, is proportional to 1 over n instead of 1 over n minus 1. Now, that's a subtle little point. I'll make a few comments about it, but we're not going to worry about it too much. Okay, so I'll say, why does s squared have a factor of 1 over n minus 1 instead of 1 over n, like sigma squared? That's a very reasonable question, okay? And so I have a full detailed answer on the course website. And so you can see the online notes for a detailed discussion. Those notes are not required reading. They're for anyone who's interested. Okay, so if you want to ignore it, that's totally fine. If you are curious and you want to see it, then that's there for you. Okay, so what I'm going to do is I'm going to try to present an intuitive argument for why they're different. Arguments. So if we were to calculate xi minus x bar squared for our sample distribution, a finite set of measurements, what happens is this average value was determined from the measurements themselves, right? They're not independent of one another. So that when I go calculate this difference, because this position was determined from these measurements, those values are artificially a little bit closer to x bar than they would be to the true mean mu, where mu would be independent from whatever our measurements were. And so because this position of x bar is determined from our measurements themselves, this difference turns out to be artificially a little bit too small. Okay, so this quantity calculates the deviation from x bar. So how much do our measurements deviate from this mean? But x bar was calculated from the xi data. And as a result, x bar is artificially close to x bar. So x bar is artificially close to the xi measurements. And 1 over n, therefore, of this type of calculation would underestimate sigma squared. And the correction factor turns out to be n over n minus 1. So what the online notes do is they go through a calculation to show you where this correction factor comes from. I'm going to go back to this picture that we had of our distribution and see if I can show you that this type of argument using a few little drawings here. So here is x bar calculated from our measurements, and it sits right at the center of our distribution. Now, if we were to keep measuring more and more and more trials, so n goes to the infinity limit, then the position of this would move around as we add more data. And in the limit that n goes to infinity, we would actually locate the position of the true mean. And so maybe for our true distribution, maybe it turns out that mu actually sits over here. And so now, if we were to calculate xi minus mu, this calculation and sum it over all the trials will be a bigger result because we have more data further away from the center than we do for the x bar position. That's the rough argument, the hand-wavy argument. Having said all of that, if you take enough trials, then this correction factor is small, and who cares about it really? So for example, in the Rukart experiment, you drop a ball and watch it oscillate. We do 50 trials. And so our correction factor would be 50 divided by 49, which is a 5% correction. And so if you wanted that to be, that would be a 2% correction. If you wanted that to be even smaller, you just keep doing more trials until you're satisfied that, you know, the correction factor could be ignored. All right. So what we're going to do now is we're going to learn something else about distribution. We're going to find new ways to calculate averages that will be useful. So we're going to talk about the mean and standard deviation of distributions. Okay, and we'll start by talking about discrete distributions. So a discrete distribution is one in which the result of an experiment can only be one of a finite set of possibilities. So a very trivial example is rolling a die. You can only get one of 6 possible outcomes. Or drawing a card, there's one of only 52 possibilities. Okay, a continuous distribution would be like measuring the speed of some electron, and the electron is accelerated through some potential difference, and you could measure any speed, any fractional value of the speed at all, and so that would be a continuous distribution. So we're going to start with discrete distributions. We're going to learn a few things about their properties, and then we're going to take what we learn and we're going to apply them to continuous distributions. That's the plan. So we suppose the result of a measurement can only be one of n possible results. Okay, and so the easy example is rolling a die. We must get one of x1 is equal to 1, or x2 is equal to 2, up to x6 is equal to 6. So there's only 6 possible outcomes. So if we make a total of n measurements, we will find, well, we're going to measure x1 some of the times. So how many times are we going to measure x1? We find x1 a total of m1 times. And then we find x2 a total of m2 times. And then we're going to find x3 and x4 and x5 and x6 a total of m6 times. Okay, so that's obviously true. What we would require is that if I was to sum up m1 plus m2 plus m3 plus m4 plus m5 plus m6, that total must be n, the number of trials, because we can't have any trials that are not one of these outcomes. Okay, so we require that if we were to sum the MI values for all of the possible outcomes, we would get n. So in general, if we had little n possible outcomes, then this would be the general rule. So for this example, n equals 6 in this case. So in this example, little n is equal to 6. Okay. So what I want to do is I want to go back to our expression for the mean and see if we can rewrite it in terms of these m quantities, the number of times we get a particular outcome. So for a large number of measurements, so n large, the probability of measuring xn is Pn is the limit as n goes to infinity of. So let's suppose I did this rolling the dice And I measure x6, m6 times out of a total of n trials, then how would you estimate the probability of getting the result x6? You know the answer is going to be 1/6, right, for a fair die. But let's suppose that our die is not fair, right? It's weighted in some funny way. So how could you express the probability of getting x6? Yeah, m6 over. Yeah, that's right, m6 over n. And so maybe if it's a weighted die, like maybe instead of getting 1/6, we get something like 13. Maybe 7/12, right? Which is, sorry, that would be a 1/2. What would be ones? So 6 out of 36 would be 1/6, so maybe we get 7 out of 36 or something like that. Okay, but that's exactly right. So the probability of getting result xn is the number of times that we actually get that from our set of trials. And of course, this only works, it doesn't work if we have only a few small number of trials, like 4 or 5 trials. It has to be a huge number of trials compared to the number of possible outcomes. Okay, so let's see. How could we express mu? Mu is equal to the limit that n goes to infinity of 1 over n times the sum of xi, where I equals 1 to n. So I'm going to try to rewrite this in another way. What I'm going to say is that's the same thing as the limit of n goes to infinity of, I'll put a 1 over n here. All right. And so then we just have to add up all of our trials, right? So in the first trial, we got x1, and then the next one we got x4, and then we got x3, then we got x1 again, and then x6. Another way of doing that is saying, okay, I'm going to get x1 m1 times. And so instead of writing x1 plus x1 plus x1 m1 times, I can just say m1 times x1. And then I'm going to get x2, a total of m2 times, and then we just keep going until we exhaust all of the possible outcomes. Okay, good. So what I'm going to do now is I'm going to distribute the n to all of these terms. And so we're going to end up with, well, I could write this as the limit as n goes to infinity of m1 over n times x1 plus m2 over n times x2 plus and so on, m6 over n times x6. But we just said that the limit as n goes to infinity of m1 over n is the probability of getting the result x1. This would be the probability of getting x2. This would be the probability of getting x3. And so the result, therefore, is p1 x1 plus p2 x2 plus and so on plus p6 x6. This is the probability of getting x1. All right. How are we doing time-wise here? Oh, we got lots of time. Okay. So that means, therefore, instead, we could write mu in a new way. We could say it's the sum over xj pj, where j is going to be 1 to little n. So we have to be careful now, because now this is a sum over the number of possible outcomes rather than the number of total trials, right? So there's a distinction between big N, the number of total trials, and little n, the number of possible outcomes. So this, just to emphasize, is the number of possible outcomes of our experiments. Okay. So sometimes this is written as P of xj. So instead of writing pj, sometimes people will write this as P of xj. So this, in either case, what we mean by this notation is the probability of measuring the result xj. Probability that a measurement results in outcome xj. All right, we could go through the same sort of derivation and apply it to the standard deviation. So likewise, we can show, and this will be part of your second homework. And so you want to follow the same sort of argument that we just did for the mean, to show that the square of the standard deviation can be expressed as a sum over the number of possible outcomes. And then what it would end up being is xj minus mu times P of xj. And so these are our two key results. And what I want to do is I want to manipulate this one a little bit. Okay, and so let's see if we could learn something about how we can manipulate these sums. All right, we're gonna end up doing a lot of, sorry, what am I missing in this? I'm missing something, what is it? Squared, yeah, that's right. I went through a whole big thing about how if you don't square it, that sum will be 0. Okay, so in this course, we're gonna end up like, it's a lot of data analysis, error analysis type things. And we're gonna get a lot of these types of sums that either go over the number of trials of an experiment or the number of possible outcomes. And so we'll often want to do some manipulations of these sums. All right, so yeah, go ahead.
Is the limit, like, do we just assume the limit is there, like, you're still taking large n?
So this probability only works when n is large, but strictly speaking, the limit is not there because what we had to do is, in order to write this as P1 is not just this ratio, it's that ratio in the limit that, so the limit is kind of contained in this probability thing. Yeah. So that's a good question. All right. So let's see if we can manipulate this a little bit. So manipulation of our sigma squared expression. All right. We have a square in here. So the first step is, all I'm going to do is expand the square. So sigma squared would be equal to the sum of j equals 1 to little n of, okay, we're going to have xj squared minus 2 mu xj plus mu squared. Okay, so if we expand the square, that's what we get, and then we multiply by the probability of getting xj. All right. So what I like to remind people of in this course is that integration is just a fancy way of writing out a special sum, a special kind of sum. It's a Riemann sum. It's in the limit that, like, some quantity delta x is going to go to 0. However, you know, it's just a fancy sum. So all of the things that you can do in integration, right? If I have the integral of f of x plus g of x dx. I could write that as the integral of f of x dx plus the integral of g of x dx. I can distribute the integral. I can also distribute the sum. So I have a sum of 3 terms here. I could write this as a sum of 3 different sums. In an integral, if I'm integrating c times f of x dx, where c is a constant, I can pull the constant outside this integral. Here, I'm going to have a sum of, say, 2 mu times x, where the sum is over the index of the x. The 2 mu is a constant, so I can pull that outside of the sum. And so those are the kinds of things that we're going to do. Okay, so let's distribute the sum. Okay, so sigma squared would be equal to the sum of j equals 1 to n of xj squared times p, right? So I still have to times by p. And then we'll have plus the sum of j equals 1 to n of minus 2 mu xj p of xj. And then we'd have plus the sum of j equals 1 to n, to little n, of mu squared times p of xj. Okay, so there we distributed our sum. Now what I'm going to do is I'm going to pull constants out of the sum. Pull the constants. Let's see, minus 2 mu and mu squared outside the sums. Okay, usually we could do all of that in one step, but let's do this slowly for this first example. Okay, so if we did that, we'd get sigma squared is equal to, there's nothing to do for this first one. That's still the same. And then let's see, the next one, we have a minus 2 mu. Minus 2 mu that we can pull outside. And then we have xj, p of xj. And then we have plus, let's see, we have a mu squared that we take outside. Sum of j equals 1 to n of p of xj. All right. So now what we're going to do is we're going to be a little bit clever. We're going to interpret some of these sums. What is this last sum going to be? Yeah, so what this is saying is take the sum of the probability of getting x1, x2, plus the probability of getting x3, plus the probability of getting x4, and so on, all the way up until we get to the probability of getting xn. And so we add up the probabilities of getting all of the possible different outcomes, and that has to be 1. Okay, so this has to be 1. This is the probability of getting, when you sum probabilities, it's like asking, what is the probability of getting A or B? And when you have that or condition, it's always adding probabilities. Probability of getting x1 or x2 or x3 plus and so on. And so on, or xn minus 1 or xn, right? And so that obviously has to add up to 1. What about this next sum? What is this thing? If you look, just look back a page or so up in your notes. Yeah, that's exactly what we just calculated for mu. Okay, and so this next sum is mu. And what we have, therefore, is that sigma squared is equal to the sum of j equals 1 to n of xj squared p of xj. And then we have minus 2 mu times mu. So that's minus mu squared plus mu squared times 1. And so overall, we get a minus mu squared. And so this is another equivalent way of writing our standard deviation in terms of mu and the probability of a particular outcome from our discrete distribution. Okay, yeah.
Since sigma squared here to find the true standard deviation, we have to square root the whole sum.
So yeah, if you wanted just sigma,
Yeah.
you'd square root all of this, including the minus mu squared. Yeah, that's right. I just didn't want to keep writing big square roots, and so that's why I'm writing as sigma squared. Okay, so that's pretty useful result. But it applies specifically to these discrete distributions, and most like physics experiments are going to result in measurements that could have any possible value. So like, what kind of experiment might you do? You, again, going to the Ruppert experiment, you measure the period of oscillation of a ball. But there's no set of discrete possibilities. That period could be anything from a continuous range of possible answers or measurements. And so how do we take this and apply it to continuous distributions? Okay, so continuous distributions. Okay, so for a continuous distribution, P of X is a so-called probability density. Okay, so if I was to draw just some arbitrary probability distribution, it might look something like this. It doesn't necessarily, I wasn't trying to draw a bell curve. It doesn't have to always be a bell curve. It could be some asymmetric distribution. So we'll draw, well, let me see if I can make it more asymmetric. Let's make it obviously asymmetric. There we go. Okay, and so what does a probability density mean? A probability density, you may have done some of this in like Physics 200 or something like that. It's going to give us the probability of measuring a result between X and some other value, like between X1 and X2, or between X and X plus delta X, something like that. Okay, so for a normalized P of X, the area under P of X versus X plot must be 1. Okay, so if I was to add up this total area underneath this curve, I would want that to be 1. And if it wasn't 1, then I would go through some normalization procedure to force it to be equal to 1. Okay, so then what I could do is I could think about, well, if I have a little slice of area here where I'm going to say that this position is X and this position is X plus delta X, so that the width of this thing is delta X, then what I could do is I could say, well, the height of this is going to be P of X. Let me call this XJ, actually. I'm going to put little subscripts J here. Okay, now I could then approximate this area as the height of the rectangle, P of XJ, times its width, delta X. Now, it's not a perfect calculation because it's not a perfect rectangle, but if I made my delta X smaller and smaller and smaller, then approximating this as a rectangle gets to be a better and better and better approximation. Okay, so the probability of measuring a value between, let's say xj and xj plus delta x is given by the shaded area which is approximately, whoops. Well, it's just P of xj times delta x. Okay. I think, is that right? Yeah, that's right. So now what we could do is we can go back to let's go back to this expression here, and we said mu is the sum of all of the possible outcomes times the probability of getting that particular outcome. And what we've just said is the probability of getting this particular outcome is given by this expression. So if I was just to multiply by xj and then sum over all the possible values of xj, that would have to be equal to the mean. Okay, so what I want to do is to say that, so if we did n measurements, we will get a result between xj and xj plus delta x. How many times will we get that? If the probability of getting this outcome is P of x times delta x, and we did n measurements, how many times am I going to get a result between these two values? No, it's not that complicated. So what we're going to say is this product is the probability of getting x between xj and xj plus delta x. So if that's the probability of getting the result and we did n measurements, then I expect to get mj is n times that probability, right? Okay, so then what we could do is we could say, all right, then mu we know is going to be the sum of this mj times the probability of getting, sorry, what do I want to do? It was just mj times xj, right? That's all it was, I think. Sorry, I'm getting confused. Let's just verify. So where was it? Mu was, here it is. The sum of the probability times x, okay? That's what I wanted. So here it is, the sum of the probability times x. And so this would be, why does this not look right? And so, right, it was mj divided by n times xj. That's what I wanted. But now mj is just all this stuff. And so, sorry about that. That was a little bit not as smooth as it could have been, but we finally got it. The probability times this xj, but now the probability is given by this funny expression, and so it's going to be j equals 1 to n of, let's see, xj, p of xj, delta x. And so you brought up, is it going to be an integral? And so this final result for mu will be an integral because we're going to have to take the limit that delta x goes to 0 in order for this calculation to be accurate. And so finally there in the limit that delta x goes to 0, we would have mu is equal to the integral of x p of x dx. And if this is a continuous distribution, then the integral would be over all the possible values of x, which could be from, well, depending on if x could be negative, or maybe it has to be positive, so it goes 0 to infinity. And so maybe what we should do to be the most general is to say that this integral is over all values of x, over all x. Okay, good. So what we'll do next time is we'll finish this off, and then I've got a couple of examples that we can do where we can actually put some of this stuff into practice for our continuous distributions. So before we do that, what do you think the results for sigma squared would look like for a continuous distribution? Yeah, it's just going to be the integral. It's going to look exactly like this, except that we're going to have a dx tacked on to the end. So for the standard deviation, we would get sigma squared would be the integral over all x of x minus mu squared p of x dx. Okay, good. And that's where we'll stop for today. What we'll do on Wednesday is the first thing we'll do is we'll say, all right, sometimes when I make a measurement, like I'm going to measure x, but I'm going to use that to calculate something, right? I measure the speed of the electron, and then I use it to calculate its kinetic energy or its potential energy or whatever it is. So how can I modify this so that I could find not the average of x, but the average value of some function of x after I do repeated measurements? Okay, so that's what we'll start with next time. And then we'll do some examples where we actually put some of this into practice. All right, good. Thanks very much.